So we will begin the last section, last lecture of the Song He. He will give the lecture on the surfaceology.
Thank you. Great. So let's continue. So due to lack of time, I'll skip things about nonlinear Sega model altogether, but mainly tell you about gluons. But before that, let me finish what I started last time. So where do this zero and factorization come from? It's literally like one line proof from string integral. Okay? I mean, I give you the sketch, which is like one sentence. So look at this F polynomial. This F polynomial depends on a lot of y's, right? So the y's are all intertwined here. So what's special about choosing this rectangle with all the c's set to 0? Once you choose that, remember this is from like all the Cij between where I is between 1 and a minus 1, and j is between a and n. When you choose all those c to 0, you kill a lot of this F polynomial. So in the formula, a lot of F polynomial drop, right? Of course, you are still left with a lot of F polynomial. But remember, really the key thing is here that this variable dya, because I'm choosing a here, this is x1a. This variable dya, it has ya to the alpha prime x1a. It has many F polynomial that could depend on ya. Okay? I leave it as an exercise to you that when you set all the c to 0, those F polynomial depend on ya all drop here. Okay? So it's very nice that this range of c exactly covers all the Fij, every Cij in this range, their Fij depends on ya, and only them. There are no other F polynomial depend on this. So you're left for this integral, you're left with this, right? I mean, there are of course many other integrals, dy over y, y to the x, the F polynomial of those y. They are still there. Fine. This integral is 0. So you're done. So this is the one-line proof of the 0 I promised. Okay? And it also tells you why it's 0. Why it vanishes also for all the c within this rectangle for all the c equals negative integer. Because what's a negative integer do? If your F polynomial is not killed, if c is 0, your F polynomial does not drop, but it's just some 1 plus y blah blah to some integer power. And if you feed it here, it's just a big sum of this kind of thing with some shift n, right? It's still 0. This is like a scaleless integral that for one variable. So this is really the key. When you set all the c to 0, you are separating. You're picking out a particular integration variable in your surface, which makes the whole thing vanish. Now if you say, okay, let's take one step back. Let's recover one of the c. Right? It's still easy enough. Let's just consider the case when all the c's are 0 and one of the c are non-zero. Integer is similar. Integer case is similar, but just even a 0 case. Now you have exactly one F polynomial of this ya with minus c. That's still there. And the rest, right? So now it's not 0. If you turn on one of the c, you are left with this one-fold integral that has ya to x1a and exactly one F polynomial. This F polynomial could still be very long, but the dependence on ya is always simple. It's always 1 plus something ya plus something else, right? It's at most that. So you compute this integral. Just compute this integral. Do a small change of variable. This integral give you gamma x top. This is x top. This is x bottom. This integral give you gamma x top, gamma x bottom, divided by the sum of them, which is this c star in the denominator. Okay? So that's the one-line proof of the factorization near 0. You see, when this is turned off, of course, it integrates to 0. When this is turned on, it does not integrate to 0, but it integrates to a beta function. And not only that, the rest of the integral naturally, because not only when you turn off those C's, not only this variable become very special, for other variables, it naturally got divided into two classes with some shifted kinematics. So that's how factorization works most cleanly in this string integral. Okay? So yeah, I spent almost an hour explaining to you this zero and blah blah, but then the proof is really 1 minute, because the structure is really so clean, right? I mean, of course, there's still some detail you can work out. For example, when the C's are non-zero but integer, and the last C is not even integer, a generic C, now it's not just a simple factorization into two things with a beta function. Now it's a summation of terms. Okay, so there's the stringy factorization for integer case is more complicated. It's not a single beta function times A up, A down, but really a sum of beta function A up, A down with different integer shifts. Okay, but the phenomena is exactly the same. Now you still complain, right? You still complain. You say, okay, this may explain phi cube. Phi cube, you can find many ways to realize this zero and factorization. How about nonlinear second model and Yang-Mills? Now I give you again a 1-line, well actually 3-line argument that this is true. Consider this integral for 2n point, okay, at tree level. So remember, the tree level integrals starts its life like that. For 2n point, this will be changed to 2n minus 3, not n minus 3, right? Alpha prime 2n minus 3. A 2n point chase phi cube integral. Now, just it with this beautiful deformation factor. What is it? It's a u even divided by u odd raised to some power. You may wonder where it come from. I'll say it in a second. So u even means like u24, u26, u46, and so on, right? U odd means u13, u15. Yeah, this is also why we have to consider 2n point, because yeah, this u even over u odd is very special for 2n points. Raised to this delta power. So of course, when delta is 0, by the way, this is the main content. The zero factorization and this unity of the three theories is the main content of this paper. You can go there for more details if you want. So if alpha prime delta equals 0, of course we know this is our chase phi cube, chi amplitude, our favorite chase phi cube theory. Now I'm telling you this now the general claim is that if you deform it by a generic, this parameter is a generic real number, positive, negative, doesn't matter, but not integer. So if you deform, if you put a vector raised to some generic parameter, it gives you nonlinear second model in the alpha prime to 0 limit, of course. Okay? So let me say it this way. Even with this deformed parameter, what is this integral? It's still your stringy trace phi cube. It's still your disk integral, only at a shifted position, right? So this whole integral equals the curly A alpha prime 2n point evaluate at what? I mean, I hope everyone still follow me. All the x even is shifted to x even plus delta, or the x odd is shifted to x odd minus delta, and all the x even odd is unshifted, right? So viewed as a string integral, it's the same function. I didn't do anything. I'm shifting this exponent by some delta, and only some of the exponent. The even guys shifted by plus delta, odd guys shifted by minus delta, and even odd guys unchanged. You may wonder, where do this shift come from? It comes from this consideration that if you want to have 0 for amplitude, you already have 0 for phi cube. So if you want to explain 0 of other amplitude, you better keep the C unchanged, right? Because the 0 conditions are formulated in terms of some C. If you deform your phi cube amplitude to some other amplitude which preserve all the C, then there's a chance that I mean, not a chance, then it's guaranteed that the deformed theory will also have those 0, because the C conditions has never been changed. The C has never been changed. And remember, C is given here. So if I shift the x even and odd in the opposite direction by the same amount, C will never change. And you can actually prove, although I give you a special ray-like realization, if you go to any realization, if you shift in this way, all the C, not only in this ABHY realization, in any base triangulation, all the C will be unchanged. So it's guaranteed that this amplitude has the same stringy zero as the original trace phi cube, because it's just the same function with C unchanged, right? So I still set those C in the rectangle to 0 or integer or one of them turned on. They still factorize. They are the old function evaluated at some shifted position. The real magic is that this shift gives you new theories in alpha prime to 0 limit. So the alpha prime to 0 limit of this shifted amplitude is totally different now. Unshifted case, it gives you phi cube. Now shifted by a generic parameter, it gives you nonlinear integral model. And when alpha prime delta equals plus or minus 1, it gives you this YMS, Yang-Mills scalar amplitude, which scalars are in pair. Okay? I haven't explained why, but I hope you get the idea that in order to explain why these two theories have the same zero and splitting as the original phi cube, it is wise to consider this kind of a shift because they preserve all the C. So the shifted theory, even at finite alpha prime, will exactly share the same zero and splitting. So I'm actually predicting infinite families of amplitude at finite alpha prime that has the same zero and splitting. The only problem is what are their physical interpretation. Now I'm telling you two physical interpretation. If you're shifting by a generic value, you go to alpha prime 0, you get a pile. If you shift them by plus or minus 1, this integer, you get pairs of scalar representing gluon. You may ask, what about other integer? You get something with higher spin particles, which are not really physical, but you can still get some. So there are infinite, at least, I mean, even forget about pion case. You do this shift plus or minus, you do this shift at any integer value, you get also a bunch of amplitudes satisfying 0 splitting. It's just that their physical interpretation is less clear. Only when it's 1, the shifting is 1, we know it's a spin 1 particle, okay? So I'm not going into detail about how this works for Yang-Mills, nonlinear integral model in particular, and how, nonlinear integral model are factorizing into 2. As I mentioned, if the two guys are odd particle case, they become the mixed amplitude, and how this generalizes to all loop. That's all in our paper if you're interested. I mean, in particular, we have worked out how this rule are also realized at the Lagrangian level. I mean, there's a nice paper by Nima and Carolina on that. So the fact that nonlinear integral model are contained in phi cube can also be realized at the Lagrangian level so that it apply to more general observables, not only amplitudes, right? You can guarantee to see this relation in general. And I just say one word that this shift at the generic value give you nonlinear integral model is also very expected from what I told you about this theory, right? Because you are not shifting any even odd pole. And that's all the pole a nonlinear integral model amplitude can have, right? So remember, nonlinear integral model amplitude has only even vertices. So all the pole looks like even odd. Because odd or even poles correspond to odd factorization, like factorizing into odd particle times odd particle. That's absent for pion scattering. For pion scattering, you have to go to an even odd pole to factorize into 2 even point amplitude, okay? So very good, I'm not shifting them. But I'm shifting all the other poles. Also very good, because I'm killing those poles, right? So start with a trace phi cube. Sorry, so I forgot to say this, that one last thing I'm gonna say about nonlinear integral model is this. Like, you just send delta to infinity of your original phi cube amplitude to endpoint where where you have this shift. It's already the nonlinear integral model to endpoint amplitude without any stringy things. Remember, this is a formula that works actually to all loop level, but already at tree level, I'm emphasizing that you don't have to go to the string trace phi cube, take alpha prime to 0, because I'm shifting the thing to a generic value anyway. So alpha prime to 0 just means delta is sent to infinity, even at field theory level. So that's why we say nonlinear second model amplitude are literally contained in trace phi cube without the stringy, right? Without the word stringy. So I'm not going into detail, but you can see that trace phi cube amplitude, when you send delta to infinity, it kills all these poles. This poles first become massive with weird alternating mass square, plus or minus, but then delta is infinity, so it kills everything. The only thing you need to study is that, this implies the Adler zero of pions and the correct factorization. Then it follows, everything follows. So actually the proof that all loop pion amplitude at the integrand level follow from this shift. Now at loop level, you also need to shift the loop puncture, call it even or odd. You need to sum it over the possibilities. But the fact that it follows from this shift, take delta to infinity, you already get your all loop pion amplitude is essentially trivial. Once you discover it, the proof is very straightforward. You just show that it has every expected pion factorization pole, including single cut and so on, as before. But when there's no pole, it's already shifted away, right? There's no, so it doesn't contain any unphysical pole. That's it. There's a very simple proof that pion amplitude are literally containing phi cube. And as I said, you can also understand them from Lagrangian. Very good. Yeah.
First of all, so the statement you're saying is that no matter what value of delta I take, I land up on the same theory.
Very good. Yes. Yes.
And also, so the fact that I'm sending delta to infinity, I guess, simplifies things by erasing Euclid's statement. But at the same time, it's equivalent to sending delta prime to infinity, right? So
No. So let me say it this way. So if you shift your if you use this shift to like delta equals integer 1 or 2 or so, it really changes this singularity structure. It makes the dy over y, for example, into dy over y square, as I will say. That's the Yang-Mills case, right? Or dy over y cube if you shift it by 2 and so on. So you cannot directly obtain those shifts at integer value from the field theory phi cube amplitude. But if it's a generic value, it doesn't matter. It's really just where you call your x. So when you send alpha prime to 0 limit, it's literally like, okay, forget about this string amplitude. Just first take this guy, because it's a generic value. First take this guy to alpha prime to 0 limit. What is it? It's just some phi cube amplitude at x even shifted by this and so on. Okay, fine. Because delta is generic, I'm already here. Now, since I'm taking alpha prime to 0, in order to recover the alpha prime to 0 limit of the shifted guy, I have to take delta to infinity to make the whole thing, to compensate it, right? So that's why pion amplitude is really the limit of field theory phi cube with delta to infinity. This doesn't work for delta being integer. Yes?
So we set alpha prime to 0 already, and
then you take delta to infinity. Yeah? At the field theory level, you are shifting the field theory amplitude and take delta to infinity. And as I said, okay, sorry, let me give you one example before I move to gluons. One example for the pion. For example, I already told you the 4-point amplitude of phi cube is this, right? Forget about the beta function. You don't need beta function. Here you just shift x13 by minus delta, x24 by plus delta. This is the shifted phi cube amplitude without stringy, just the shifted phi cube amplitude. Now, you ask me, what is the delta to infinity limit? Sorry, I forgot to put some power of delta here. I'm really extracting the non-vanishing order of this expansion, right? So I put delta to some power. I forgot which power. Let's work it out together. So the leading order cancels. That's the crucial thing. You have minus delta and plus delta, so the leading order cancels, right? So expand to the next order. The next order gives you x13 plus x24. That's your pion amplitude, as promised. All right? So this expansion is extremely easy to work out. So to be more precise, really, at leading order you get 1 over delta 1 minus 1, and at next order, so you need to put a delta square here anyway, delta square in front of everybody. At next order, 1 over delta square, you actually get a minus sign and then x13 plus x24. Okay? and plus higher order, but you're extracting the leading order. You're multiplying whole thing by delta square and take delta to, infinity, and you get the pion amplitude out of it. Let me leave you an exercise. So here is the expression for 6 pion amplitude. Do this exercise, it's very simple. Write down the Catalan number, the 14 terms for the phi cube. Okay? So if you remember the 14th term for phi cube, it can look like 1, 3, 1, 4, 1, 5, right? Plus cyclic, and so on, and also like 1, 3, 1, 4. Sorry, let me see, 1, 3, 1, 4, and 4, 6, plus cyclic. That's already 12 terms. And then finally, you have this interesting term that's 1, 3, 3, 5, 1, 5. That corresponds to a triangulation like that, right? 1, 3, 5. And the plus cyclic. These are 2 terms. So this is a very interesting exercise, very interesting nonlinear second model. That's the last thing I say about nonlinear second model. Take the 6-point phi cube amplitude. 12 plus 2 terms. There are 14 terms. Do this exercise, do this shift. Okay? What's this shift? X 2, 4, 4, 6, 2, 6 will be shifted by delta, and the 1, 3, 3, 5, 1, 5 be shifted by minus delta. Do this shift. Do not touch 1, 4 or 2, 5 or 3, 6 because they are the 3 unshifted guys. Do the expansion, as I said. Now you probably need to multiply by delta cube, not delta square. Anyway, you do this expansion, you find the first non-vanishing order is what I give you here. The pion amplitude with x14 still as pole. This other things become numerator as the 4 point. And then with this contact term, just the linear in x contact term is coming from this 2 term. Okay? So as I said, once you discover it, this proof is very simple based on recursive, the factorization and the recursive argument, right? So in the remainder of my time, I'll just tell you the story about gluons. And the key thing is really you not only get tree-level gluon amplitude, which is actually just the bosonic string from here, but you really get all-loop gluon amplitude. There's still a lot of things we can study, but you really get all-loop gluon amplitude by that shift. Okay? So any question for this zero splitting and nonlinear second model part? Great. So let's move to gluon. So I'm also going to skip the bosonic string argument, but let me just say it in words very quickly that if you start with a 2n point bosonic string amplitude, not the phi cube string amplitude, which has this kind of Kobayashi factor, you know, like Zij raised to alpha prime Sij, but also some vertex operator like epsilon I dot epsilon j, Zij square, you know, this kind of thing, epsilon I dot kj, Zij, it's a summation. Yeah, anyway, if you look at this bosonic string amplitude and you extract the component that all the epsilon dot, let's call P, all the epsilon dot P is 0, and only epsilon 1 dot epsilon 2, epsilon 3 dot epsilon 4, and so on are non-zero, then you discover our shift. This 2n gluon amplitude at this special kinematics corresponding to exactly this picture that 1, 2 is in a pair of scalar, they are the coefficient of epsilon 1 dot epsilon 2 for the gluon. 3, 4 is the coefficient of epsilon 3 dot epsilon 4 in a pair. 5, 6 in a pair, and so on. Okay. So this is how an alternative way of deriving your shifted formula. So you may wonder why when alpha prime delta is 1, I get a 2n scalar amplitude. This tells you the reason. The reason is that the amplitude in Z language looks like this: Z12 square, Z34 square, and so on. Z2n minus 1, 2n square. Okay, just one term. And then you have this product of ij, Zij to the alpha prime Sij. D and Z over SL2. Okay? So this shifted formula, I mean, it's still not obvious here, but let me write it one more. Let me write it this way. I put the Park-Taylor here. Remember, this is the, and I put the Kobayashi here. This is what we talk about a 2n point, sorry, not dn, d2n, right? A 2n point phi cube amplitude times this ratio. Because my n pairs of scalar amplitude has this factor instead of the Park-Taylor factor. So I need to multiply this ratio, z23, z45, and so on, divided by z12, z34, and so on, right? This ratio. What is this ratio? Anyone familiar with what I told you about the definition of uij, right? I think I erased. Will recognize this ratio is nothing but u even divided by u odd. Okay? So at tree level, there's really no guesswork. There's nothing deep, and you don't need to use surface or anything. It's literally computing the bosonic string amplitude where you have pairs of tachyons interacting with gluons, or pairs of scalars interacting with gluons, because that's the worldsheet picture gives you. That formula tells you, okay, anything is, I mean, any formula can be written as this way, but in particular, this formula tells you that the Park-Taylor, this is our stringy trace phi cube, right? This is, if you want, this part can be written as our dy over y product of u to the x now. Now, this part, since it's u even to u odd, is really doing the shift in x, right? So it's u even, u odd, with alpha prime delta equals 1, very importantly. You see that when delta is 1, to relate it to your question, when delta is 1, it's really changing the singularity structure. It's changing this z12 to square, z34 to square. So that's why you cannot obtain it as NLSM. So at tree level, we derived y alpha prime equals 1 is giving you this YMS amplitude with pairs of scalars coupled to gluon. So you already at tree level, you can say, okay, I'm done. I succeeded in extracting gluon amplitudes out of 2n scalar amplitude with this shift. How do I do it in the last step? I take a residue, right? I take a residue of S12 goes to 0, S34 goes to 0. In our language, we would say X13 to 0, X35 to 0. So I take multiple residues, residue X13 to 0, X35 to 0, and so on. Of this 2n point delta equals 1 shifted amplitude. I do this. Sorry, this is hard to see, but let me erase. Let me do it here. Sorry. So once I take this residue, this is the idea of scaffolding. Okay? So now I do scaffolding. Because you may wonder, yeah, this is computing bosonic string with gluon in between, but it's still not a gluon amplitude. It's 2n scalar amplitude, right? How do I get n gluon amplitude out of 2n scalar amplitude? Very simple. I go to this pole when P1 plus P2 is square to 0. This pole, and so on, right? So that's the residue. So this is the scaffolding idea. You have a pair of scalar, you call it P1 and P2. They become a gluon. This becomes your gluon 1. And this gluon has the momentum K1 that's equal to P1 plus P2, right? This gluon has this momentum, and it has a polarization. Now polarization emerge because this polarization is given by P1 minus P2, as you're very familiar from the 2 scalar 1 gluon interaction vertices, right? So it's really saying the gluon polarization is treated this way because this vertex is really G on mu's, P1 minus P2 mu, right? This is the interaction vertices. In other words, I'm writing down this formula again. For 2n point, I have my dy over y. I have my 2n minus 3 dy over y integral. I have my product of uij raised to alpha prime xij. And I have my shifted thing like u even divided by u odd. This whole amplitude, I'm further taking residue. I'm taking the product of residue at xii plus 2 equals 0 when I is odd. Okay? This gives me something that looks like n gluon amplitude, but with the polarization given by this formula, right? So this is how you extract, and then of course you still take alpha prime to 0. I mean, this, before you take alpha prime to 0, this is really a bosonic string amplitude with n gluon interacting with pairs of scalar. Now you take the residue and take alpha prime to 0, you get n gluon, Yang-Mills amplitude. At tree level, it's guaranteed because it's derived from string theory. But now we want to argue that this factor, because this factor now is defined to all loops, right? For all surfaces, we can, we have to be careful about when all surfaces, for the internal guys, they all correspond to the odd puncture. But other than that subtlety, this factor is defined for all surfaces. So now that's why we can expect that a slight generalization of this formula to all surfaces should work. So that's the main conclusion, that if we use this original formula for all surfaces, remember this formula gives you stringy trace phi cube to all surfaces, right? Now we insert a deformation parameter, insert a factor u even divided by u odd. That also is defined for all surfaces. And then we take a residue. We take the external residue. So look at the surface. The surface now look like that. There's some internal n-gon surface, and then you have your gluon going out like that, right? So this is the scaffolding idea, really in the fat graph. That now you have your scalar 1 and 2 that's responsible for gluon 1, scalar 3 and 4 responsible for gluon 2, and 5 and 6, and so on. 2n minus 1 and 2n. That's for gluon n. Okay? So you're really taking this residue at x13, it produces you gluon 1 and so on. Now, yes?
We don't have to worry about any spurious contribution from the quartic interaction of the scalar.
Very good. Because we take this residue. Before we take a residue, this amplitude itself, before you take this residue, this amplitude itself has all contribution from those other vertices. But once you take every pair of scalar, you take their own shell residue, you are going to the internal n gluon thing without any pollution from other vertices. It's obvious, right? Because every pair of scalar, there's no phi cube interaction anymore. It's just 2 phi coupled to a gluon. So once you take the residue, you get a gluon, on shell gluon. And the on shell gluon can only interact with each other according to the Feynman rule of Yang-Mills, not Yang-Mills scalar anymore, right? So all I'm saying is external gluons only interact as in Yang-Mills theory without creating some scalar line in between, right? Any other questions?
What is the order of operation?
Yeah, you have to take the residue first. You take the residue, you get something that's still finite alpha prime, and then you take alpha prime to 0. Yes. Otherwise, it's the same as what I explained about the pounds, right? After you take alpha prime to 0, you lose it. You cannot extract those shifting at integer values. Okay? More questions?
A bit conceptual question here. So, are we guaranteed that for loops it converges?
Converges in what sense?
The sum converges. So one of the things that we expect from field theory is that we're actually dealing with asymptotic series, and we.
Oh. So here I'm talking about loop integrands as rational function, just like tree amplitudes for gluons, right? Mm-hmm. So I mean the only convergence you might worry is that at loop level this product of u to the x will be infinite in general. But I will tell you that precise prescription that it's truncated. You only need to include finite number of curves in order to extract the
right. So the factorial growth of the diagrams will actually not.
That's not the problem. Yeah, that's very very good question, because this is always like a single term, like a single integral formula for any number of loops. Of course, when you take alpha prime to 0, concretely, in practice, I never said that practice this is easy to do. When you take alpha prime to 0 for any of this, even tree level, it's a very daunting task to work it out explicitly. But there's no issue of like packaging all the diagrams in one formula is correct, right? I mean, the remarkable thing is that we're considering stringy trace phi cube, and this simple u even over u odd factor will allow you to produce gluons after you take these residues. Yeah, but the alpha prime to 0 limit in practice is of course difficult. So that's why in practice, I mean, maybe in the end I will mention a more practical way of producing new data for loop integrands, all loop integrands in Yang-Mu theory would be recursion. The recursion use this surface idea to compute their residues, but in practice, you don't need to take alpha prime to 0 limit of this. Of course, it would be very nice to learn how to do this, like really yeah. Any other questions?
Do we need to worry about scalar lines in the loops? Because for Yang-Mu scalar...
Very good, very good. I'll come back to that. So for loops, it's, yeah, I said it too quickly. For loops, there are really some subtleties because now you have the UC to the XC where the C can be self-intersecting, the C can be closed curve. You need to deal with that, and that also solves your problem. So there's some prescription I will give you at loop level. But before that, let me first say something even kinematic-wise. Why would you expect some n? So as I said, I mean, the picture is clear, right? Okay, you get some n gluon amplitude where gluon has not only momentum, Ki, but also polarization epsilon I, and you say, okay, my epsilon I is chosen to be that. From this point of view, it's fine, right? But we're really now expressing things in terms of 2n gone x variables. So it might sound weird that your Yang-Mu's amplitude now doesn't look like Yang-Mu's amplitude at all. It looks like some 2n scalar amplitude. Although you already take some residue, it's still some scalar function, right? Just function of xij for the 2n gone. Very weird thing. So I want to emphasize this point that it looks like that, right? So we have a 5 gluon amplitude. We scaffolded it. So we really should start with 10 scalar amplitude, which has 1, 3, 5, 7, 9. These are my internal gluon pentagon. But now I scaffolded with some punctures with some mark point 2, 4, 6, 8, 10, they will play the role of like the polarization degree of freedom for the gluons. So the gluons has pose like, I mean, this kind of pose, x odd, would be gluon pole, right? It's within the gluon pentagon. And this in particular, x13, x35, and so on are 0. This is my scaffolding residue that I took here. In order to make these pairs of scalar on-shell gluon, I have to turn x13 to 0, x35 to 0, and so on, right? Now, what about those other curves or chords here, like odd to even or even to even? They will be my polarization, Lorentz product involving my polarization. Actually, I can tell you that x even is roughly speaking, like x24 is roughly speaking related to epsilon 1 dot epsilon 2, for example. And x even odd, say the even is 2 with some odd, will be related to epsilon 1 dot some k dot some gluon momentum. I mean, it's a rough idea, but the key thing I want to ask here is, okay, forget about you know this from bosonic string. Also, when you generalize loops, you don't know it from bosonic string, right? What kind of property do our curve integral give to make it really a gluon amplitude, even to all loop order? What kind of property? To understand that, we have to first explain two things in this language. One is gauge invariance. Gauge invariance plus linearity in polarization. The second is factorization. Let me go very quickly those. And you will see that exactly this formula will guarantee those two properties. Okay? So since I'll be very brief, I'll just give you the polarization, the gauge invariance first. The gauge invariance plus multilinear. These are very basic properties of gluon amplitude that you thought it's actually multilinear. I mean, everything is multilinear in epsilon. It's linear in every epsilon. That's like a definition, right? But from this point of view, it's not clear at all. I mean, if I hand you some rational function of this x, 2n-gon x, how do you know it corresponding to a gauging? I mean, how do you translate it into a gluon, into the language you're familiar with epsilon and k? In general, you cannot. If I hand you a random function of 2n-gon xij, it does not correspond to gluon amplitude, right? Only when it satisfies this condition, there's a chance. So what are these conditions? I mean, this condition usually looks like epsilon 1 shifted by alpha k1. The amplitude is unchanged. This is called gauge invariance. And the second thing is that the epsilon 1, I mean, these people don't even talk about it usually. Epsilon 1 shifted by itself, by beta epsilon 1. The amplitude should be beta times amplitude. These two conditions are called gauge invariance and multilinear, right? The multilinear is really just the rescale your epsilon, the amplitude should also rescale correspondingly. Now, very nicely, in terms of x, how do they look like? If you remember, we called that epsilon here to be P1 minus P2, which really looks like this, which really looks like epsilon 1 mu will be proportional to x2 mu minus the half point, x1 mu plus x3 mu, right? So if you look at the picture, it's saying this. It's saying, what is the epsilon vector? The epsilon vector is connecting this endpoint 2 to the middle point of 1 and 3, right? This small, let me write it in red. This small arrow is epsilon 1, from the middle point of 1 and 3 to the external 2. But this is your gauge choice, right? This is just a particular gauge choice. When we do a gauge transformation, we can slide the starting point of this arrow anywhere here because you're just shifting them by the x3 minus x1, right? So it is a very beautiful story that you first build your gluon n-gon, and at every n-gon you can attach a small vector to represent your polarization, so that the endpoint of the vector becomes the even mark points, and they connect it to a 2n-gon, right? And gauge invariance is really saying that it doesn't matter where you start your vector. It's independent of that. And written in this language, I'm not going through the detail, but written in this language is really saying the amplitude and gluon amplitude now in this X language should look like x2j minus x1j times a function qj, where j, you sum it over all j. This is for gluon 1. For gluon 1, this condition. And at the same, there are actually two conditions. This condition becomes a linear combination of them. Also, x2j minus x3j times qj, where qj is the derivative of the amplitude with respect to x2j. Okay? So this is the key thing. I mean, I skipped the derivations in our paper that if I hand you a random function of xij of the 2n-gon, the necessary condition, in order for it to be able to become gluon amplitude, to be able to become a function that's gauge invariant on the multilinear in order in epsilon 1, it has to be written like that. It has to be written like x2j minus x1j. So you take derivative of x2j, but then you have to multiply by this combination or this combination, and add summing over all j, you can reconstruct the original amplitude. Okay, this is literally this condition. So if I hand you a function, you test this. If it doesn't work, it's not gauge invariant in particle 1. It cannot be written. Okay, so of course you repeat it for all n gluons. So this condition has to be satisfied. Okay. Now, very beautifully, we will see. Let me give you one more example. Say three-point amplitude. How does three-point amplitude look like? The three-point amplitude look like exactly x24 minus x14 times x36 plus cyclic. Okay? So this is also an exercise for you. The 3-point Yang-Mills amplitude, I mean, you're familiar with the usual 3-point Yang-Mills amplitude, like epsilon 1 dot epsilon 2, epsilon 3 dot some P1 minus P2 plus cyclic, right? This is your usual way of writing. I'm just saying this is equivalent to this, okay? And you can check this is satisfied gauging invariance. But a more advanced exercise would be what? Just derive this from my formula. Okay, now you are all equipped to do that. So look at this formula, right? Look at this formula in rate-like. You do it for hexagon, right? You do it for this gluon inside triangle, but then you inner triangle scaffolded by 2, 4, 6. This is 1, 3, 5. You do this hexagon, you plug it in, but remember you have to multiply by this factor. You take the residue of 1, 3, 3, 5, 5, 1 to 0, this triangle. Now you have nothing to do. Now you don't need to take alpha prime to 0 or anything, because this is a 2n minus 3-fold integral, which is 3-fold integral. You take 3 residues, you are done. Okay, I forgot to say, I'll say in a second that the residue of external xij to 0 is equivalent of taking some y residue inside the integral, right? So this 3-fold residue will localize this 3-fold integral. You literally end up with this. Okay? I leave this as an exercise which would be very fun to do. No, you have to learn everything to even derive this. Okay? But now, how do you guarantee this is true for any number of points without a bosonic string argument? How do you guarantee it's true for n gluons, that the formula is gauging invariant, and even for all loops? That's the next thing I want to talk about. The argument is actually very simple. We will see that we don't need to rely on any detail about this formula or the bosonic string kind of argument, which won't exist for loop level anyway, as far as I know. But we will see that very general point guarantees the gauging invariance of our formula to all loop order. Okay? The point is the following. The point is that, first of all, I want to remind you this U fact that probably not very, I didn't get a chance to talk yesterday that, okay, so this U even divided by U odd factor is nothing but product of 1 over yi for scaffolding residue. Sorry, for scaffolding triangulation, okay? So you need to fix the base triangulation, and I choose to fix it to be anything within this n-gon, but for the outer gon, I have to do this. So I've already shown you many times, right? Like there. So, sorry, let me erase this lines. So I need a base triangulation, a very natural one that turns out to be mostly useful for our gluon scaffolding problem. Is you first take your 2n-gon, you do this. You do this n-gon. This is already part of the triangulation, right? You triangulate, like you already chosen n chord. Now you do whatever inside, for example, like this, for your inner gon. That doesn't matter. So your y would involve y13, y35, and so on for the outer guys, and then some other y odd inside your n-gon. Doesn't matter. So that's your base triangulation. I'm claiming, do not have time to prove, but I'm claiming that this factor is exactly this. So this gives us a very beautiful language that is, you just do dy over y squared if it's a scaffolding triangulation. In other words, out of the 2n minus 3 dyi, n of them are already fixed to be y13, y35, and so on, and the other n minus 3 I don't care. So really, my gluon amplitude is dy over y squared. Then exactly the same uij, xij, because my shift is done by this square. Okay? So that's really the last thing, that's really the cleanest thing I can say about the gluon formula. So phi cube, yeah, if you didn't follow the last hour, you can pay attention now. The phi cube is dy over y with this factor. Gluon is dy over y squared with this factor. That's it. Of course, you still need to take a residue x13 and so on equals 0 to extract the angle 1. But this is the key. This squaring is the thing. I mean, intuitively, it's very simple, right? I think there were questions before about if you look at the surface integral, I told you x equals 0 is very easy. X equals 0 corresponding to the corresponding to the residue of either u or y goes to 0 of that curve. So the surface factorized and so on. So I think one of you asked what about x equals -1, -2, and so on. It's very, very good question that basically it's the same. So you still have the the factorization of your surface, but now you need to take derivative. When x equals -1, you need to take a derivative of y. When x equals 2, you need to take 2. So this derivative is reflected. This derivative is reflected in this square. Okay. So instead of taking just the usual scalar factorization, this square guarantees that you have a spin 1 particle propagating. But it's precisely this square produces your gluon, you still have to prove. So for example, yeah, now this is the formula this is the takeaway message that in a scaffolding triangulation, this is your gluon amplitude with alpha prime to 0 limit, at least at tree level, an Young Muse. I mean, at tree level, you also know before you take alpha prime to 0 limit, this is the bosonic string with n gluons. But now we'll generalize to all loops. And before we generalize to all loops, let me explain why this squaring guarantees gauge invariance. Okay? No scalars. I mean, the formula looks like a scalar thing, right? It's all xij, but the physics is really n gluon amplitude. There's nothing. I mean, if you view it this way, I'm really forgetting about this picture of bosonic string with pairs of scalar and so on. I'm really giving you a new formula in terms of 2n gone xij language. This is the new formula that produces you n gluon. Now I'm gonna prove you that it's gauge invariant and it factorizes correctly. That's it. Yeah. It's gone. After the residue is all gone. I mean, first of all, at tree level, it's trivial that after I take the residue, within the internal n gluon, there's no scalar pollution. That you agree, right? And I think Yang asked the question that if you go to loop level, the scalar might pollute running in the loop. But now I have to give you the prescription of this UC to the XC. How do you choose this, especially close the curve, to kill the scalars in the loop? I mean, the scalar in the loop is really a dimension-dependent thing that people asked the other day. So our formula for trace phi cube has no dependence on space-time dimension, right? We just assume it's large enough, there's no gram determinant. But for gluon at loop level, you have to tell me where is the dimension dependence. Exactly because within the loop, after you take the polarization sum in the loop, there's a dimension dependence. So this is a formula. I encourage you to look at the paper. It's a very beautiful general argument that this kind of U even to odd to all loops for any surface. Yeah, for any surface, you have to remember this odd puncture also refer to the loop puncture, because if you look at the word of the loop puncture, it goes like an odd puncture as the external thing. This is like a topological fact. This has nothing to do with the detail of how you triangulate your surface, how complicated your surface are. This is always true. For scaffolding triangulation, this is always true. So that means that to all loops, this measure is very, very universal, right? You don't have to worry about. There's a chance that this will work to all loops. But first thing first, let's talk about tree level. Remember, in this scaffolding residue, let's look at gluon 1. Gluon 1 live here. And this is my scalar 1, I mean, my external, like this road I call 1, 2, this road I call 2, 3, this gluon 1 road I call 1, 3, right? So when I produce my gluon, I really need to take the residue of x13. Usually I take the residue of x13. It's very simple because it's a dy over y. I just take that residue on y. Now it's dy over y squared. So now I have like dy13 over y13 squared. How do I take a residue of y13 goes to 0? I mean, I'm taking residue of x13 goes to 0, but that corresponding to because of Koppen-Nielsen factor, taking the residue at y13 goes to 0. It's also very simple, right? Here I have my product of u to the x. I mean, here I have y to the x and so on. Well, I have u to the x, which contains y to the x. In order to take this residue, I need to find the term that's linear in y13, right? y13 times anything plus higher order terms. I need to find this part that's linear in y13. That's my residue, okay? So in other words, what are the u variables that depend on y13? First question. Second question, what are their derivatives with respect to y13? Because I want to extract the linear piece, right? So this linear piece really looks like summing over ij d log uij dy13 times the rest, right? Now, you will see our surface study yesterday now pay off, that any curve that could depend on y13 must go like that. Either it's a 1 to some j, or it's a 2 to some j, right? Remember, this curve is 1 to j. This curve is a 2 to j. Why? Because that's the only two curves that pass 1, 3. This is true for any surface, not only tree level, okay? For any surface, you have to start either from 1 or 2, reach at somewhere, but you have to pass 1, 3. Okay, so this derivative simplifies to derivative u2j, derivative log, how do I write it? Like x2j, derivative log u2j y13 plus x1j, I mean there's a summing over j, right? Within the sum I have 2j derivative of 13 and 1j derivative of 13. It becomes this combination. Okay? Now again, I probably don't have time, but let me just tell you that you can show also from this curve, the width I told you yesterday, that u1j times u2j is independent of y13. Okay? So you just work out that matrix, work out the 2 by 2 matrix. You denote the remaining part of the 2 by 2 matrix A, B, C, D. You do the last 2 by 2 matrix multiplication. You will find that u1j and u2j, in this product, they cancel. So that just means that this two derivative is the same up to a sign. So derivative of u1j, u2j with respect to 13, the product of them is 0, right? So I can simplify this formula to 2j minus 1j derivative u2j derivative y13 times the rest, sum over j. That's it. This is my qj, where it's the amplitude take derivative with x2j. Okay? So there's also this formula, you have to change the coordinate to show the second formula, but that's the gist of showing gauging invariance for the surface, now for any surface, without restricting to tree, right? And in the final minute, final 2 minutes, let me also say the same is true for factorization. Okay? So this is gauging invariance. I recorded here. But the same is true for factorization. What do I mean by factorization of gluons? So gluon amplitude factorization is really saying something like the residue of amplitude at xab equals 0 of an amplitude, n gluon amplitude. It's not just a left times a right, but it's really a left with some derivative of x, let me call it small xj, and a right with some derivative of small x prime, x of x prime, capital J, times a gluing factor. This gluing factor looks like j capital J minus jb minus a capital J, summing over small and capital J. Let me give you the picture here. The factorization for gluons really look like that. If you have a chord AB, you have left and right. The indices here run through left. I call it this small j, and the indices here I call it capital J. The factorization really goes like that. It goes like you have some left amplitude, but you also have another point here. This is like scaffolding. internal gluon, okay? And also you have this side, the right side, I mean, this is still small j, capital J. This is A and B, A and B. Now you have X prime, okay? It's really saying, unlike scalar factorization, you just have left times right. Now it's spin 1. You have a spin 1 particle propagating, which can be viewed as with this auxiliary scalar scaffolding, and they are epsilon mu, epsilon nu replaced by eta mu nu, dot, dot, dot. This gluon say sum is replaced by this factor. Okay? I don't have time to derive it, but this is as important as this gauging invariance condition. Now, this formula, if you take a residue at XAB goes to 0, what would happen? It's very similar to doing gauging invariance. When, to showing gauging invariance. When showing gauging invariance, you see, because of this y square, you have to take a derivative of y13, right? Now, because of this y square, you have, when you consider XAB residue, because it's squared, this square is the key, you have to take the derivative of YAB, assuming AB is your part of your base triangulation. And without going into any detail, I just want to say that you can find in our paper, I think is a very good exercise to look at this formula, take XAB residue, which would mean that you have to acting with this YAB derivative on it. Very similar to the gauging invariance argument, you will see that anything past AB must take this kind of form. So you will derive this formula. Okay, I don't have time to derive it. So that's all. That's essentially everything for tree level, right? Although I said the gauging invariance and factorization property also generalize to loops, but I haven't given you a precise prescription for the loops. So that's the last thing I want to say. Any questions so far about the tree case? So let me emphasize again that you can derive the tree formula from this bosonic string point of view. That's in practice is very useful. You further take the residue explicitly. In our paper, we show that you take this scaffolding residue explicitly, you recover the vertex operators of the bosonic string. You just recover the original formula in the Y language very, very nicely. So there's nothing wrong with it. But the logic here, let me emphasize again, the logic here is that we want to find the n-gluon formula from 2n scalar that's universal for all surfaces. And that's how we find it. We have to view it really in terms of this form. So you have exactly the same surface u to the x picture, but you change your D-log form into this. That is all why gluons are much harder than phi q, right? Why I'm saying this is still an ongoing problem. For example, the alpha prime to 0 limit of this non-logarithmic form is very difficult to take. But I mean, there's still a lot of things we can learn. And how can I convince you that this is universal? I convinced you by showing that just this simple change of dy over y into dy over y squared guarantee gluon gauging invariance and gluon factorization, all in this new language, right? I'm not using epsilon at all. I'm talking about gluon polarization in terms of this 2n gone stuff. Now, the last thing I haven't told you is that this formula, although I argue that by showing it to square, it looks very universal, I haven't told you precisely how it generalizes to all loops. Because it cannot exactly be just the change of y into y squared. There must be some, so this part is similar. This part is exactly the same. You need to take alpha to 0 limit to get n-gluon, I mean integrand of n-gluon at L loop, for example. Yang-Mills amplitude, you have to take this limit, you have to take a residue of x13, 35, and so on to 0. You have to choose a scaffolding triangulation. Now you have your dy over y squared. This I hope I convinced you has to be there. Now, here's the thing. What do you take to uc to the alpha prime xc at loop level? Let's go back to phi cube. For phi cube, if you only care about field theory limit of phi cube, this is extremely easy to take. You just take anything that's no self-intersecting, no closed curve, is just the simplest thing, like tree level, right? The finite number of things, it's guaranteed that it gives you the correct field theory limit, the tropical limit, ABHY, generalized to all loop, okay? If you want to recover really loop level amplitudes, loop level string amplitudes for phi q, I think it's still work in progress, but at least one loop is clear that you have to take infinite. You have to take all the self-intersecting curves with infinite number of windings. So the U equation really has to be satisfied with this infinite product and so on, right? So at all loop level, this is something that's still left to be shown that for all surfaces, this gives you some tachyon amplitude to all string amplitude, literally, okay? Now for Yang-Mills, it's something in between. Obviously, you can think of like, we are not so ambitious of creating an all loop string amplitude for gluons. We are not there. We don't know how to do that. So we don't want to include like literally infinity, right? But we can also not just be very stupid as taking the scalar amplitude, which has no intersecting and so on. So it's really something in between. So it has, say for one loop, in this product, you have to include those self-intersecting once curve, okay? So it's like, here you have your loop puncture, you can have this kind of things. You can have external guys can go like this, or it can go like wind around once and so on, okay? So you have to include those. And there's a very important curve that so far I didn't show you this curve, which is very important when you compare to really all loop, even one loop bosonic string tachyon amplitude, right? This closed curve, okay? So this closed curve, naively you say, okay, the closed curve has no momentum. It's homologous to the boundary, right? But the closed curve is the only, so you still have to include this self-intersecting curve with its own x, and you include the closed curve, let's call it delta. At one loop, there's only one delta. And what do you put here? This is related to the question about dimension and also scalar pollution and so on. You have to call this delta, the exponent of delta, 1 minus your space-time dimension in order to produce the correct one-loop Yang-Mills amplitude. Okay? So the dimension dependence in your formula is reflected in this exponent of the closed curve. So with this starting point, you just look at your one punctured external endpoint curve surface. This formula with this square again guarantee you have surface gauging invariance, surface factorization, and this very beautiful single cut. Okay, so if you go there, if you go to a curve, this x equal to 0, you're reproducing chi amplitude with 2 more punctures, chi gluon amplitude. Okay, so it's very let me draw it properly. Like you really go to this thing with a puncture scaffolding here, and this thing with another puncture scaffolding here. Okay, so there's literally we literally derived the formula in actually not in that long paper of January, but in August, the short paper, we give the precise formula for how one loop amplitudes factorize and go into single cut using this one loop formula. Of course, there's an all loop generalization. The difficult thing is how do you take the residue and take alpha prime to 0. So that's why I think currently the state of art is that you use recursion based on this residue that surface factorization tells you, okay? So you basically know every residue there could be, even at tree level, you could derive Yang-Mills tree amplitude recursion for any number of gluons, not like BCFW, but because that really works in 4 dimension in particular, but this is like in this 2N Gauss language, the all multiplicity recursion relation for Yang-Mills tree, but also for Yang-Mills loops. That's the current frontier, that how do you derive some all loop Yang-Mills recursion based on this surface idea, because we still haven't learned how to effectively take such field theory limit of the non-logarithmic form. Okay, I think due to lack of time, I'll stop here, and thank you for your attention.
Please ask questions.
Okay. I think I'm asking too much questions, but is there a way to give bounds on the integrals? So if we're not really interested in evaluating the integrals for higher loops itself,
Yes,
but have some bounds on the absolute value of the integral.
Oh yeah, sure. So I should say there are many. Okay, so not particularly in this setting, but already in the original phi cube amplitude, it's a very interesting question of how do you numerically evaluate such. I mean, not only giving bounds, but really, for example, starting large n is really giving a very good estimation of how the amplitude behave when n is very large. Also, at loop level, there's works by Giulio and others that you can turn this formula in alpha prime to zero limit, turn the tropical limit formula into some integrated amplitude formula. So with the Stringer parameter and so on. That's also a very good starting point for doing numerics, for doing this things. Yeah, I forgot to mention that I mentioned one open question, which is how do you really derive gluon amplitude? But already in the phi cube case, there's tons of open questions about how they really give you a practically useful, even like related to what Sebastian has been telling you, that for every single Feynman diagram, you have some way of extracting UV divergence, IR divergence, and so on, based on Newton polytope and so on. Now you have a formula, a tropical formula that combines all Feynman diagram into a single object. How do you extract the physical, extract the number out of this kind of out of this formula, right? That's very important. And I take the opportunity to also mention a few other open problems. Like, for example, we don't even understand anything about how supersymmetry. So how, first of all, related to the question in the first day, that we don't understand how to add matters, for example, like how to couple to fermion, couple to general Lagrangian. So there's some understanding of, in the tropical world, of turning any Lagrangian theory with any Lagrangian colored particle, with any Lagrangian into a tropical formula. But it's not as if we understand how gluons couple to fermion in QCD in standard model in this kind of realization. And in particular, if you want to do superstring, there's no way, so far as I understand on the surface, like you can, already at tree level, if you translate the superstring correlator into this language, just like you did for bosonic string. Bosonic string has one term, and in the recent paper with Tree and others, we translated the superstring formula, which already teaches us a lot of things, but there's no intrinsic understanding of supersymmetry in this world. Of course, the biggest direction I would say is go to uncolored particles. That I have not much to say, except that there are uncolored particles in the trace phi cube story, which is this related to this closed curve, right? This uncolored sigma particle, like the closed analog of the closed string, emerge from this open string world. But you can also think about something very simple, like already at tree level, how do you understand BCG relations? Like in this language, it's very hard to, it's very different than the usual story that now your worldsheet, because everything at tree level, I fixed this to this 1, 2, and to end this ordering, right? So if I change ordering, it will correspond to not this positive space where all the y's are positive, but some u become negative, some y become in other region. So how to incorporate this, how to go beyond this colored particle, even before go beyond the colored particle, go to other orderings, and understanding this before you squaring anything is already very interesting. Yeah. So there are many things I think would be very interesting to explore. Yeah.
Any other questions? If not, let's thank the speaker again for the very great lecture. Yeah, we will have a lunch and we will meet again at 2 p.m.